Hello, and welcome to the session on evaluating mass airflow sensor data. So this right here is a GM Delphi hot wire mass airflow sensor. And on any of the vehicles that run an mass airflow sensor, this is going to be the primary input for calculating fuel delivery. Obviously, we need to know different engine operating parameters, so different RPM, different load. We need to know how much air is coming into that engine so that we can calculate the proper amount of fuel to inject. And if the values coming from this mass airflow sensor are not accurate, then our fuel delivery is not going to be accurate. So it's really important that we can look at this and either with a scan tool or we can do a visual on here. I'll show you kind of a quick visual inspection on this, kind of determine, hey, do we have a good mass airflow sensor or not? So first thing is a visual inspection. So if we look at this, we can look at the hot wire elements in here. We can make sure that there's not ash or dirt deposits on them, especially if we had a vehicle that's operating in dusty conditions or maybe hasn't had proper service maintenance done on the air filter, or we had an air cleaner issue or it was pulling dirty air, anything like that, and we could have deposits on here. How these hot wire mass airflow sensors work is essentially a little heated wire suspended in the airflow, and the more air that goes by it, it pulls heat away faster. So therefore it takes more amperage from our little mass airflow sensor circuit board here to maintain the temperature. So this mass airflow sensor looks at and says, hey, the more amperage that I need to put through that wire to maintain temperature, well, I must have more airflow moving past it. So it uses that correlation to determine airflow. So if we have any dirt or ash over top of that wire that's insulating it, that will reduce the amount of heat coming off of that wire, and it will keep the hot wire hotter, which this mass airflow sensor circuit board will look at and say, hey, I don't need to put as much amperage through that to keep the temperature there, to keep it hot, so we must have less airflow. It's going to communicate that to the engine control module, which is going to say, hey, I got less airflow, I'm going to put less fuel in, and we end up with a lean condition and various drivability problems because of it. So that's one of the first things I usually look for, is make sure, hey, if we got a hot wire mass airflow, are elements clean? They sell mass airflow sensor cleaner, aerosol can, you can spray it on there and clean them off. A lot of times that works pretty well. Another thing that we're going to look at, not all mass airflow sensors have them, but this one has this honeycomb on the inlet side, and these are very important. I've seen people that have removed these thinking that they're going to get better airflow through them, but this actually is very important that it's undamaged and intact, because what this does is it straightens the airflow, so it's all traveling in a straight direction before it hits those little heated wires. If that air is swirling, very often a lot of cars use the corrugated air intake ductwork, the rubber ductwork, and that will get the airflow kind of swirling and turbulent. It will remove, or it can remove, the heat faster from those wires than if the airflow is very straight and what we would call laminar. And if we have turbulent flow, okay, instead of laminar flow, and it's removing more heat, this mass airflow sensor is going to look at that and say, hey, I've got more airflow than what's really occurring, and we might actually run into a rich condition. Okay, so just a quick visual on this. Is it there? Does it look like somebody's removed it? Or is it really damaged? Did somebody get real rough with this, or he's bent over? That can give us issues with either turbulence or lack of flow issues as well, or that the flow is not even across it. It can really skew that airflow sensor in any direction, just depending on the specifics of the damage. So, two quick visual things. Okay, the third thing that I'm going to look at is with a scan tool, with that vehicle warm, fully up to operating temperature, and at idle, I'm going to look at the grams per second indicated by the scan tool from the mass airflow sensor. And if this was off of, let's say, a 6-liter engine, well then at idle, with the engine fully warmed up, I want to see at least 6 grams per second of airflow. Okay? Now this is just kind of a good rule of thumb. if I've got 6.3 grams or if I've got 5.9 grams, I'm not going to just, make a diagnosis solely on that. But it gives me a good idea. If I see 2 grams and it's a 6-liter engine, I know there's something up. I know that for some reason, we are not measuring a proper amount of airflow going into that engine, right? So that's the third way I can do it. Now, at higher RPMs and higher loads, it gets a little trickier because I can't take and just off the top of my head say, okay, at 4,000 RPM, at 80% throttle, and 15 inches of mercury manifold pressure, what airflow should I be? Should I be at 85 grams per second or 105 grams per second? I don't easily, I can't give you, and the service information is unable to give you a number based on that. Sometimes they will give you a number. They'll say, okay, at wide open throttle before the 1 to 2 shift, you should have a certain grams per second of flow. But again, that's going to be kind of a guideline, a rule of thumb. It's not going to be a very precise indication. What I'm going to show you today is a technique to get a more precise measurement of the airflow sensor capabilities or the accuracy of the airflow sensor at various loads and RPMs. Okay? So for some vehicles, we're going to do it at wide open throttle. For some vehicles, we can do it at park heavy throttle, just depending on the situation or the vehicle configuration we have. And we'll talk about that a little later. But this is a very efficient, very straightforward procedure, and again, can save you a lot of time and money. And we can pick up some of these mass airflow sensors that may be degraded. They're working, they look okay, but the values are a little low, which can cause various issues. So, for example, if this mass airflow sensor was maybe reading 15 or 20% low, but it responded and it looked good on a graph. We looked at the graph, as we increased engine RPM, the airflow went up, looks okay, but our numbers were 10, 15, 20% off. I could run into lean conditions, which could end up giving me some fuel trim codes, different drivability problems, hesitations, rough idle, that type of thing. I can also run into transmission problems because airflow is a major indication of engine load, and on an automatic transmission, our engine load or airflow is going to be a major input for mainline pressure. So if this sees less airflow coming in than what is really coming in, there's a good chance our mainline pressure is going to be running a little bit lower than what it should be, and over time this can have a negative effect on the durability of our transmission. Also, it can affect our shift points and shift feel and so forth as well. So this sensor here really can affect a lot of different things. So we want to make sure we've got good data, good values coming from this.
Okay, the next thing I want to talk about are the two different ways that we can calculate the airflow, or the ECM will calculate the airflow in a modern fuel control system. The first is a pretty simple method. So we talked about the mass airflow sensor, and that mass airflow sensor is going to really put out a signal that is directly proportional to our airflow, and the computer is going to pretty much directly use that in its fuel control calculations. So based on the signal coming from the mass airflow sensor, the computer will know, hey, we got 65 grams per second or 10 grams per second, depending on the operating conditions. So that's pretty straightforward. The second way is the speed density calculation, or the speed density method. And that's a little bit more, little less direct method, but it's still pretty straightforward. I'm going to go through and talk about just kind of how the computer is going to use this. This is going to help us evaluate our mass airflow sensor. If we understand this speed density calculation, we can use it to our advantage to help us double check our mass airflow sensor. Even if we have a vehicle that only has a mass airflow sensor and does not have a map sensor, and therefore doesn't use the standard speed density calculation. So the way this is going to work is the computer is going to be looking at the intake air temp, the manifold pressure, RPM, and then obviously we know engine displacement that's programmed into the computer beforehand. And with these values, it can determine how many grams per second of air is coming into the engine in a speed density calculation. So I'm going to look at, the next thing I want to look at is how that calculation takes place. So if we were to look at a single cylinder, okay, we can apply the ideal gas law formula, which basically tells us the relationship between pressure, volume, and temperature. And I'm not going to go through all the details in here, but essentially if we know the pressure in the cylinder, the volume of the cylinder, the temperature of the gas in the cylinder, or the intake air, we can calculate the amount of air in that cylinder, so the mass or the weight of the air in that cylinder. And that's really what we need in those fuel calculations, is we need to know the weight of the fuel or the air so that we can calculate how much fuel needs to be injected. So this is really the bedrock of that speed density calculation, is this ideal gas law formula. So if we look at a single cylinder, and we can kind of just imagine it's a single cylinder engine even, really doesn't matter if we have a 5.7 liter 8-cylinder engine or if we have a 5.7 liter single cylinder engine. This calculation is going to be the same. Obviously it's going to be split up between multiple cylinders, but this will still give us the airflow, the overall airflow into the engine. So I'm not going to go through the calculations on it, but I want to talk about kind of where we get these values from. So in order for the computer to do this calculation, it needs to know the pressure, the volume, and the temperature. So temperature, we'll start there. That's pretty straightforward. Intake air temp. When that piston comes down on the intake event, it's going to draw air in from the intake manifold, and it's going to be approximately the temperature of the intake air temp. Obviously, as it comes into the cylinder, it's going to heat a little bit, but the computer can use that intake air temp to gauge what the temperature of the air in there will be. This R value is just a constant, so we're not going to talk too much about that. The V volume, that's just simply displacement. So when we come down on this cylinder, again, if we assume just a single cylinder engine, it's just the displacement of the engine. If we wanted to get a little more precise, if it was a 5.7 liter engine, we just take that and divide it by 8, for example, if we had 8 cylinders, and it would tell us a single cylinder displacement. I think kind of the most interesting one to look at is the P, or the pressure. So if we think about it, the highest that pressure can be in a perfect world, the pressure in that cylinder after the intake event is going to be equal to the pressure in the manifold. And so we're really going to be looking at manifold absolute pressure to get this pressure number. So if we have, let's say we're at light throttle cruise and we've got 10 psi pressure in the manifold, in the intake manifold. So that would be, approximately 20 inches of mercury would be our pressure in there. We can only get that amount of pressure in the cylinder. Okay, that's the most we can get. We cannot get atmospheric pressure under light throttle because we don't have atmospheric pressure in the manifold. Now if we go to heavy throttle or wide open throttle, that pressure will obviously increase. As manifold pressure increases, the maximum pressure in the cylinder would also increase. Okay, so if we take that ideal gas law formula and reformulate it, and again I'm not going to go into the details of how we would do that reformulation mathematically, but we end up with this. We end up with this formula. So we kind of jockey things around here a little bit. Now the units are changed, so we've got some correction factors in here that make the units a little easier to handle. We don't have to do as many conversions out in the shop, which makes this a little more efficient. we've got so two different conditions here that we need to deal with, or two different types of systems. So if we take a I would say a typical GM product where we have a mass airflow sensor and a MAP sensor. If we have a MAP, then we can take a look at it at any engine load, okay? Because at any point in time, we know what the mass airflow sensor is telling us, and we also know what the MAP sensor is reading for manifold pressure, and we know RPM and all the others. So we can plug in the MAP value, and that's going to be in inches of mercury, the displacement of the engine in liters, the RPM. We've got our correction factors here, this 0.177 and the 459.67. We plug in the intake air temperature in degrees Fahrenheit right here. And we're going to get an F calculated number. So this is the calculated or expected airflow in the engine, and it's going to be in grams per second. Then the next thing we can do is, on a vehicle like that, we would also have our mass airflow value, and we would just simply take the measured airflow divided by the calculated airflow times 100%, and that would give us our mass airflow indicated volumetric efficiency. So this is what the volumetric efficiency is of the engine according to the mass airflow. So this F calc is kind of an idealized, or in a perfect world, this is how much airflow we should be getting into the engine under those manifold pressure, RPM, intake air temperature conditions. The F measured is what the mass airflow sensor is actually measuring. Now, normally there's going to be a discrepancy there because, as we know, volumetric efficiency on a naturally aspirated engine typically does not, at least a kind of a stock engine, nothing that's been performance modified, our volumetric efficiency is not going to be 100%. Okay, we expect that. So that is going to be taken into account. So we would normally be looking for something in this 80% range, which is pretty typical. The other thing that this is going to account for is discrepancy in our mass airflow signal. So let's say we have perfect volumetric efficiency in our engine, so we're at 80%, what we would expect, but we have a dirty mass airflow sensor that's reading less than expected. Well, it's going to show up here in that our expected, or F calc value, is going to be much higher than our F measured. So when we do this calculation for volumetric efficiency, or mass airflow indicated volumetric efficiency, we're going to get a low number. So if we are down below 70%, really, we should be really looking for mass airflow issues or airflow issues in general. Because if we do have issues with either intake or exhaust restrictions, possible valve train problems, that can throw off the actual volumetric efficiency, which could cause this number to be lower. But 9 times out of 10, if you've got a low volumetric efficiency number here on most late model stuff, we're probably looking at a mass airflow sensor discrepancy, either a degradation or a dirty elements, the hot wires on it. So this gives us a really good picture into what's going on. Now I want to back up here and talk about naturally aspirated engines and wide open throttle. So if we have, I use Ford and Mazda are two good examples. They ran a lot of mass airflow sensors with no MAP sensor, and in that case we could say, well, we don't know what the manifold pressure is at any given point in the manifold, so we can't do that speed density calculation, and therefore we can't really use this method to evaluate it, right? Well, we have a workaround in the fact that at wide open throttle, the manifold pressure, we can expect it to be at or very near barometric pressure. So what we can do is, if we grab all of our values at wide open throttle, we can assume that MAP is equal to baro, and we can plug barometric pressure in our formula for MAP. So we would use this formula right here. Okay, we would go through to the same calculations, and then we would compare that to what we're getting on the mass airflow and find our mass airflow indicated volumetric efficiency just the same as on any other vehicle. If we have a forced induction vehicle, so turbocharged, in that case, we probably are going to have a boost sensor. So if we have a mass airflow and a boost sensor on it, we will know the pressure in the manifold, and we can use this middle formula right here. Because obviously on a boosted vehicle at wide open throttle, we cannot make the assumption that the manifold pressure is equal to barometric pressure. I have some data pulled up here from a GM 3.8 liter. Kind of show you how to go about getting the data points that you're going to need to kind of evaluate the speed density method or to input into the app. So this is with a snap-on scan tool. We're pulling it into ShopStream Connect to get all of our data points here. But you can definitely do this with a different type of scan tool. Most scan tools are going to have some type of a functionality where you can record the data and then go back after the fact and pick a data point and get different values at a specific point in time. And that's what you're going to want to do here. So the data PIDs, or the data points that we want to really focus on, are going to be RPM, intake air temp, mass airflow, and map. I do have TPS up on here just to give us some perspective as to where we are at as far as throttle opening and so forth. So we want to pick some point, and it's not real particular where we pick, but I want to pick some place where generally we're accelerating. We don't necessarily have to be at wide open throttle since we have a map sensor. Now, if we were doing a mass airflow, a vehicle that only has a mass airflow sensor, then we would have to pick a wide open throttle part. So I'd be looking in this area right here. We're at 99% throttle, and I would be getting the values at that point. And along with that, I probably would want to do a little bit longer wide open throttle run than this. It was a pretty short time. You know, if you get 2-3 seconds at wide open throttle, usually that's pretty good. So we've got our point that we're going to pick here, and then we simply can go down the line and look at it. And so at this point in time, our current RPM was 4,012. Our mass airflow was 125.78 grams. Our manifold pressure, now it's showing 277 here. So this would be more than likely, there's a decimal missing here, so it's just 27.7 inches of mercury, okay, for our manifold pressure. Sometimes when you pull it into ShopStream, you lose a decimal. No big deal. So we know that would be 27.7 because atmospheric pressure is approximately 29 to 30 inches of mercury. So we've got all those values. Intake air temp was at 21 degrees Fahrenheit here, so we need that as well. So there we've got all our values. We can input them into our speed density formula or into our app and use that to evaluate our mass airflow sensor. The next thing I'm going to go through here is kind of an example using the app. So we talked about how the kind of the backbone or the basis of this method, and you've got the formulas on how to do this if you want to hand calculate it. But in a shop setting, you know, time is money. We generally want to be efficient. So we've got this app that we can use that makes it more efficient, saves time. We don't have to worry about calculation errors. So on the app here, first thing I want to point out is on the top, we've got an instruction for use. We can get specific instructions if we've got a vehicle with a mass airflow only. So, you know, think Ford or Mazda. And we can also get specific instructions if we've got a vehicle that has a mass airflow and a map sensor. You know, think GM. And it'll kind of walk you through these instructions just the same. So in this case, I do have a map sensor on it, so I'm going to select that yes, this engine uses a map sensor. The only difference is if I select yes, we get an extra entry box here for map value. It still does list barometric pressure here, but the calculations are going to use our map value rather than the barometric pressure value. If I were to click no, we can see that that map box goes away, and now we're going to be using barometric pressure instead of map value in that speed density calculation. So I'm going to click yes again because we've got this GM 3.8 liter that uses both map and mass airflow. So first thing I'm going to do, I can click in displacement. I'm going to just simply type in, 3.8. Okay. Barometric pressure. So I could look this up in a weather report if I wanted to, if I needed barometric pressure. Now on this particular engine, I don't need barometric pressure. If I was doing a vehicle that did not have a map, then I would need baro. But just to show you kind of how this works, I could look this up in a weather report, go online, whatever, and that would be fine as long as my units are in inches of mercury. But if I want to save some time, I can just look up barometric pressure, type my zip code in, and it will automatically populate. It's going to go out and get the latest weather report and pull the barometric pressure in the correct units, and we don't need to take the time to go out and find that value. So next box down, intake air temp. So what we saw on the scan tool data is we had an intake air temp at that particular point we were looking at of 21 degrees Fahrenheit. The map value we had was 27.7 inches of mercury, and the mass airflow value at that point in time was 125.78 grams per second, and the RPM at that point was 4,012. Okay, done. And we can just simply calculate, and we can see on this particular vehicle, our MAF indicated, or mass airflow indicated volumetric efficiency was 80.88%. That's right where we want to be. If I see that 80%, I'm good. If I'm I'm in the 70s, I'm starting thinking, maybe do we have something going on here? If I get low 70s and below, then I'm starting to really question whether I've got a degraded mass airflow sensor or not. And I have seen mass airflow sensors that were, brand new, aftermarket, out of the box mass airflow sensors that the values were skewed. And when we put a good high quality mass airflow on it, those numbers were right where they should be. So this also gives us a good way to kind of evaluate a good mass airflow sensor. Especially if we're doing transmissions and we want to make sure that the mass airflow numbers are good so we don't have as many warranty issues. This would be a good check to see that, hey, we're at least at this point when we're sending that vehicle out the door, our mass airflow sensor seems to be working good. So that load value that's going to go into setting mainline pressure is going to be accurate. So that's just one example of where this could be really valuable. But yeah, you can see really quick, really easy to do. In just a minute or two, we can punch the numbers in and have a really good look at what that mass airflow is. Because we might have a mass airflow sensor that says, "Yep, it's going up and down with with throttle position," but you really don't know whether that value is, maybe 10% lower than it should be. And this really gives us a good tool to find the answer to that question. One other thing I want to point out on here is it does also give you grams of air per intake event. So in most cases, this isn't going to be a real critical number from a normal drivability diagnostic standpoint. Here we can see we got 4.65 grams of air coming in the cylinder, or in each cylinder. But if we wanted to kind of think of it from a fuel flow standpoint, if we know that we've got 4.6 grams of air, if we divide that number by 14.7 for gasoline, because our stoichiometric air fuel ratio for gas is 14.71. So if we divide that out, we would actually get the grams of fuel that should be injected into that cylinder on each injection event at that point in time. And it could give us some ideas if we were doing performance builds as to, okay, what kind of injector flow
rates do we need to have reasonable pulse widths, and what kind of fuel flow would we need, those types of things. So maybe not going to use that on your day-to-day basis if you're just doing normal drivability work, but if you get into the performance side of things, that may be useful as well.